Do you remember the unit circle from geometry and trigonometry? Notice how I'm smiling because I know how much students hated that. So what I'm going to do is torture you with it, but I'm going to show you something very simple, at least at first sight it seems simple, about the probabilities. You can follow my little cursor around and we'll see what kind of scratchings I've done here on the whiteboard. Here, the prepared axis is plus. What does that mean? That means aligned. So the prepared axis is the aligned. Remember, there's only two outcomes, aligned and not aligned. But as we'll see here, there's different probabilities that occur when you're somewhere in between that with the measured axis. Now, this means it's prepared. It means we've selected atoms that are plus. And if we measure plus, if we measure along that same axis, we'll get plus again. And that'll continue to be the case. Okay, let's go around the radian measure of this unit circle that, boy, I just love this. I hope you do, and if not, I'm sorry, you're going to have to suffer through it. Here's the radian angle 0, pi over 2, pi, 3 pi over 2, and then we're back to here, which would be 4 pi over 2 or just 2 pi. In other words, 0 and 2 pi are the same thing. Now, here's what we reported was that we were on the z-axis and then we measured with the x-axis and it came up 50%. Follow the numbers. The numbers won't lie to you. So we got 50% aligned and 50% not aligned. Now, before we got there, if we had turned it at kind of a diagonal form, then we'd get 75% aligned and 25% not aligned. And then vice versa over here. Over here, they're all non-aligned. How can we come up with a rule to determine, based on the angle, what the probability is going to be? What do you think about this? Let's see if this matches all the rules. Cosine squared of pi over 2, not pi over 2, theta over 2, where theta is the angle around this circle, or the alignment with the prepared axis. And notice it's squared, notice it's pi over 2. First, let's look at the pi over 2 and why that makes sense. Cosine of theta over 2, where theta is 0, that gives us a 1. It's 100%. If we go over here, cosine of pi over 2, that's theta over 2, pi over 2 equals 0, and there we get 0%. Now, let's go over to the 50% one, see if that makes sense. At pi over 2 divided by 2, that would be pi over 4, and pi over 4 is 1 over the square root of 2, so if you square that, you get 1/2. Okay, now it's starting to make sense. Whoa, I've added a lot here. Where have you been? Well, I've been doing all this work. I updated things a little bit. Pi over 3 and 2 pi over 3 for the 75% and 25%. If you want to, you can work that out, but I checked it and I trust myself. Now, you can check it just to see if that's right, but it does work out. Oh, I did update this also. Rather than just plus and minus, I put plus z and minus z, just so it relates to physical space. The spin state can be represented as a ket vector. A vector, so there's components to of a vector, right? Well, we have a components which is plus z and minus z. Those can be the components. That means there's only two dimensions, right? And I've got that cosine theta over 2, sine theta, oh, wow, I've introduced that, sine theta over 2, and I'm getting really tricky here with this ei to the phi. This is the complex part of it that's necessary for us to figure all this stuff out. Because sometimes this other component has a phase difference from the first component. So that's important to describe this psi vector. Now, if you've got a ket and it's part of a bracket, then I guess you need a bra. Here's a ket, here's a bra, and the two things together make a bracket. We'll look at that in just a second here, but let's see what the difference is. Cosine theta over 2, plus z in a bra, and e to the minus I phi. Well, when you work with these brackets and complex numbers, the bra has to be the complex conjugate of the ket. And in this case, it's pretty simple. You just take the minus value to get the complex conjugate. And notice that these bra plus z and bra minus z. Okay, let's see what those do. Well, those are kind of complementary. We'll see what happens with them. Now let's take this form. This form is called an inner product. And that inner product, if you take the state vector of itself, the inner product, it better be equal to 1. Because the probability overall has to equal 1. In other words, probability of one situation or the other situation, they have to add up to 1. Just like these do. 0% and 100%, 25 and 75, 50 and 50, 75, 25. You get the idea. So what we're going to do is take this inner product. And this inner product is going to be, here's the bra, here's the ket, and it's just like back to algebra. You take these two multiplied together, these two multiplied together, and then you take the inner part of it and the outer part of it. Anyway, here it's all laid out for you. If you want to freeze the frame and look at it, do it now. Otherwise, I'm just going to talk through it. Once we multiply these things out, once you get the same basis set here, that's just going to equal 1. And the same basis set here, that's just going to equal 1. If you get the different basis sets, well, everything that's aligned for everything that's not aligned, all you do is come up with 0. So that pretty much wipes out this entire line right here. And all we're left is with cosine squared theta over 2 plus sine squared theta over 2, which, if you go back to your trig identities, that equals 1. So we met the requirement that the probability is overall 1, and we also looked at a best representation of the state vector.